accomplished within 7 years. That was very, very impressive. So, so I certainly have a lot of questions. So maybe I ask you kind of philosophy question, right? So since you are so successful in this field, what advice you would like to give the younger generation? So you are really young, but I'm talking about a younger generation, right? So what kind of advice you are going to give them to hopefully they will be as successful as you are when they become a little bit older. So
okay. So I'm not so successful. I'm not so successful. We are just starting. So so far we are okay, but I think the most important factor is that this era we enter this field in the right moment, and now we have a very good position in this industrial. We are number one in China in 3D sensing, and I believe that in next 3 to 5 years we may be number one in the world in 3D sensing in all kinds of these 5 kind of technology. So we cannot say successful, but we have a good position here. And for advice for younger generation, I think for this younger generation, students are much more intelligent, much more smart than us before. They know more. But I think one thing the students need to remember that you need to select one field, or if you want to go to academic, okay, do it 10 years, 20 years. And if you're going to industrial, select one direction and go deep, 10 years, go very deep into it. This is very, very important. So for example, I have been in this 3D field for 18 years. And if I enter this field 5 years, 2002, I entered this field. If I left this field 2007, 5 years after that, then I will be nobody. But I entered this one 10 years, and 2017, I established a company. At that time, maybe the algorithm, the optical system, everything we know, because we spent 10 years, then we know it very well, and then we have more chance to open a better world. So focus on one of the promising field and spend 10 years into it. You will be much better. Then you change several times within these 10 years. And this is my advice.
Thank you. That's great advice. So basically, what you try to give the young generation is that if they are interested in something, even though some area may not be very hot at that point, they should continue work on that and go deep. And after a while, so the moment could come, and if they grasp it, hopefully they will be as successful as you are. So
much better than me.
So you are the role model in this field. So there are quite a number of questions, maybe a little bit technical questions from the audience. So the first one is about the what is actually the biggest challenge in the field right now?
Okay, so Dr. Zhi answer this question or?
Sure. Yeah, I will take over the Q&A session now.
Okay.
Yeah, so I'm Chen Zhi from OBEC. I will answer the questions in the Q&A session. So the first question is about what's the biggest challenge in the field, right, yeah. Professor?
Yeah. This comes from the audience, so.
Sure. Yeah. I think that's a very, very big question. It's about asking the biggest challenge. So in my view, for this 3D
from technology?
Hello, everybody. It's about time to get started, so let's do it. My name is Tyler Bell. I'm an assistant professor at the University of Iowa in the United States, and it is my pleasure to welcome you to day 2 of the International Forum on 3D Optical Sensing. You are in the invited talk session. We have a lot of great talks lined up for you this morning, this afternoon, this evening, wherever you are. I will be hosting and introducing the first couple of them, and then my co-chair will get to the second half after the coffee break. So with that, let's get started. Our first talk right now is going to be from Matthew G. Finley. Matthew is a PhD student in the Holoreality Lab at the University of Iowa, and he studies signal and image processing. He has his bachelor's and master's degrees also from the University of Iowa, and his work has been featured on the cover of Applied Optics and has won Best Student Paper Awards in the past. And today, Matthew is going to bring us a talk titled Variable Precision Depth Encoding for 3D Range Geometry Compression. So with that, Matthew can go ahead, share your screen, and we look forward to your talk.
Awesome. Thank you. Yeah, can everyone see my screen? Yeah, hope so. Okay. So yeah, thank you so much for the introduction. And before I begin, I would just like to say that I'm super honored to be here and being able to present my work alongside a lot of other, esteemed and innovative engineers and scientists. So like Dr. Bell said, this work is titled Variable Precision Depth Encoding for 3D Range Geometry Compression, and it proposes a novel method for compressing 3D range data with a variable precision parameter, and that allows us to achieve file size reduction while ensuring the points of interest are well preserved within a scene. Just a few accolades about this paper. It won the Best Student Paper Award at the 3D Measurement Data Processing Conference of Electronic Imaging in January of 2020. And an extension of this work was published in Applied Optics in June of 2020, and that had some additional experiments and a more fleshed out introduction section as well. And also before I begin, I'd like to acknowledge my co-authors on this paper, Jacob Nishimura and Dr. Bell, who introduced me here. He's the head of the Holoreality Lab at the University of Iowa, and Jacob is another student there as well. But so just a brief outline of what I'm going to be discussing today. I'm going to start with some introductory material. I'm going to talk about what 3D range geometry is and why we need to compress it. And then I'm going to go into some specific motivation about our method, and then get into the principle and some experimental results that corroborate that principle. So starting with that introductory material, we first have to determine what 3D range geometry is, and 3D range geometry is a surface scan. So unlike something like an MRI that might slice through a depth range and you end up with a volumetric scan, range geometry is just surfaces. So here are a couple of examples. On the left here, we have a high precision scan of a shoe print in soil that could be used for forensic sciences or metrology. In the middle here, we have a scan of a human face that could be used for telepresence or telecommunications. And here on the right, we have some LiDAR data that could be really useful. I know that's a big topic in the autonomous vehicle scene right now, and it's able to capture large scenes very quickly. So that's what 3D range geometry is. What can it be used for? I mentioned some applications just now, but here are some more. NVIDIA just recently had a big initiative for collaborative design within virtual reality environments, where they were trying to get engineers and architects and other creatives like that into a virtual reality environment, so they could modulate 3D range data, they could blow it up, they could annotate, and they could work together without leaving the comfort of their own home. Another application that may be especially relevant in the midst of this global pandemic is telemedicine. So this is a French company, Nomadic, who proposed a system that was using virtual reality in order to interact with 3D range scans of human bodies or people that may be injured, and that could bring professionals to the patients without actually having to have them in contact. So that could help prevent the spread of disease. And so those are kind of two, more commercial aspects of 3D range geometry. But what about consumers, right? What about your everyday Joes? So Facebook just announced, actually, and just released, I believe, the Oculus Quest 2 just a couple of weeks ago, which is a very inexpensive virtual reality headset, which can allow users to interact with 3D range geometry for ever decreasing costs. So we know what 3D range geometry is now, and we know some applications that can utilize it. How do we get it? And I could go into a lot of detail about, offset projectors and cameras in, structured light capture systems or stereo vision systems or time of flight systems, but I'm sure that there will be plenty of talks later today that will discuss that in a little bit more detail. I think for this talk, it's sufficient to say that there's a lot of devices that are capable of capturing 3D data now. So for example, the iPhone and the iPad both have 3D scanners on them. Microsoft's line of Kinects is able to capture 3D data. And additionally, like I discussed previously, autonomous vehicles are capturing 3D data at a very large scale in real time. So we know that we can get 3D data, but why do we need to compress it? This talk is all about compression, but why do we need it? And I'll revisit this example of a footprint in soil that I used previously. And like I said, it's a pretty high precision, high resolution scan. So it's 1920 by 1200 pixels. And in its raw form, that's 36 megabytes of data. So that doesn't seem like a lot right from the get-go, but if you have 10 of these scans or 100 of these scans or 1,000 of these scans, it very quickly adds up. That's a lot of data that you have to store or transmit over the internet, which can quickly become expensive. Another example is the same scan of a human face that I used previously. This is a slightly more modest resolution at 640 by 480 pixels, and in its raw form is only 5 megabytes of data. And by the way, this is interesting because I believe that this is the same resolution that the iPhone scanner uses, so just interesting tidbit there. But 5 megabytes per frame, if I want to use this, the application I mentioned with this piece of data previously was telecommunications. So if I wanted to stream this data in real time at only 30 frames per second, which is a fairly modest frame rate, that 5 megabytes of raw data becomes 1.2 gigabits per second of data. And I don't know about everyone that's watching this, but here in the central United States, I can't buy internet with speeds that fast. So that's definitely a prohibitive factor for applications that want to use this technology. And so one popular approach to compressing 3D data is to take this nice 3D, high quality, high resolution 3D data and to store it into the color channels of a traditional 2D RGB image. And the benefits of that are that we are able to use mature, well-defined image compression techniques in order to further reduce the file size of our 3D data. Additionally, we're able to use mature, well-defined image processing techniques in order to modulate our data in such a way that we can even further reduce file size. The problem inherent with this, though, is that we only have 8 bits per color channel. So we only have access to 256 values with which to represent our data. So if I use this scan of a human face, and let's just say that the depth range is 100 millimeters, just for the sake of easy math, and I want to represent this data with a precision of 0.1 millimeters. I want to interact with it in a virtual reality environment or measure with 0.1 millimeters of precision. That means I need 1,000 values in order to represent this data accurately. That's a problem if I only have 256 values. So really, that's why we have to encode it. So instead of just directly storing our data, we have to modulate it in such a way that we can represent more values. So that brings us to this idea of sinusoidal encoding. So as I said, if we don't encode our data, we just directly throw it into the color channels of a 2D RGB image, we only have access to one value per pixel value. And if we need 1,000 values, we don't have enough because we only have 256 values. But if I introduce this idea of sinusoidal encoding, where I take my depth information, and let's call it Z for this, in these equations, and I put it inside a sinusoid with some other parameters. And you can see that if I have one sinusoidal encoding period, then I now have access to 2 encoded values per pixel value within our encoded image. So if I increase the frequency of the encoding sinusoid, though, and I now have 2 encoding periods, then you can see that I get 4 encoded values per pixel value, per gray value in my encoded image. And four encoded values, so 2 encoding periods, is what's required to represent this because 256 times 4 is greater than 1,000. But how do we go from 1 to 2 encoding periods? We modulate this parameter P. So this parameter P is determining the frequency of our encoded image. So it may be a bit confusing because I'm going to interchangeably use fringe width, P, which is, P is defined as fringe width, and the number of encoding periods, and those two are inversely related. So if I'm, as P goes up, the number of encoding periods goes down. And we know as the number of encoding periods increases, the frequency of our encoded data increases, right? So like I said, if we have more encoding periods, we have more sinusoidal periods, which just means higher frequency. That's pretty intuitive. And because, if we're following the example that I've used previously, if we have more encoding periods, we have access to more values, which means that we have access to more precision, but at a cost of more file size. So here's a brief experiment that kind of demonstrates this. So if I used a fixed frequency with 2 encoding periods and 6 encoding periods, we can see that I have some associated RMS errors and file size associated with those encoding frequencies. As I go from 2 to 6, I get a decrease in error, which makes sense. Higher frequency means higher precision, but we also get an increase in file size, which is usually not super desirable. So moving on to some specific motivation for our method, as I've said, all of these methods previously are using a fixed encoding frequency. They're using a fixed number of encoding periods to encode an entire scene, which can prove problematic when we have interesting geometry like this very high resolution surface scan of a crater on the surface of Mars. And this is really cool. I'm a big space nerd, so this is a neat piece of data for me. But this was captured by the HiRISE project. But you can see that there's this crater in the middle, and it's surrounded by a plane. And I don't know about you guys, but I think that the crater is really cool, and the plane is maybe a little bit more boring. But if I want to store this data, if I want to encode this data with high precision and maintain high fidelity in this crater with a fixed precision method or a fixed frequency method, I have to encode all of the scene with the same precision, which means that I'm going to be possibly wasting a lot of file size and a lot of resources encoding this plane with very high precision. And that can prove problematic when I have a specific region of interest in my geometry. So what we want to do, the whole point is to be able to encode things that we care about with high precision while relaxing that precision constraint throughout the scene. So what we do is we take this idea of sinusoidal encoding that I've discussed throughout this presentation, and then we have an additional third channel, by the way, here that's used to recover our depth information. It's used to unwrap our high frequency data, and it's stored in the third color channel. I've only talked about 2 signals so far, so this is the third one. But what we want to do is we want to make this parameter p variable. We want to make it vary pixel by pixel. And although that looks fairly easy in these equations, we just add an ij. It's really actually quite nuanced how we're able to generate this variable precision parameter. Physically or visually, this is what these look like. So we can see that we're able to vary our p for an ideal hemisphere with a range of 256. This is what that looks like with the the distribution centered about the mean depth values within the scene. And I'll discuss this a bit more in detail shortly. But our encoded signals can be seen. So I1 and I2 are these high frequency sinusoidal encodings. And then our third color channel here, our I3, is just this normalized depth map. And when we store them in a 2D RGB image, this is what they look like down here in the corner. But like I said, the problem is not storing them in an image. It's how do we generate p? How do we generate this variable precision parameter? And the problem is that we need p, this variable precision parameter, to both encode and decode our data. So in order to get I1 and I2, these high frequency sinusoidal encodings, we need a variable precision p. But in order to get our depth information back, we also need p, but we want to generate p with knowledge of our depth information because we want to encode things we care about with higher precision while maybe relaxing that precision elsewhere. So we have to play a little bit of a trick. We have to generate this variable precision parameter with an approximation of z, because we're not going to know z until we decode all of our data. So we know that this third color channel, that this normalized equivalent of our data, is going to be quantized after we store it in an image. So if we can just simulate that quantization operation prior to generating our variable precision, our variable frequency parameter, then we can recover that variable frequency parameter on the decoding side of the equation. So I know that was a lot of information. It might be a bit confusing, but visually, this is what it looks like. So we take our original normalized depth map, and we just slap it with an 8-bit quantization operation, which is going to be the exact same thing that we're going to get after we store this in the color channel of a PNG image. And from this parameter, this quantized version of our depth map, which I'll call I3 prime, we can arbitrarily, we can take some arbitrary distribution n. In this case, it's a normal distribution centered about the mean depth values in the scene, and I can map my my parameter p to our data using this quantized version of our original data. So then I can generate my sinusoidal encodings. I can store it in a color image. But the important thing to note here is the third color channel here, this low frequency signal that I recover from my encoded image, is going to be identical to I3 prime after it has been stored in image. So I store I3, but what I get back is the same thing as I3 prime. And from that, I can regenerate my variable precision parameter. So we've talked about encoding now, but how about decoding? So like I've talked about, we can use this third signal here, the normalized version of our depth map, in order to recover our variable precision parameter. And we know that all of our high fidelity data is stored in I1 and I2, these sinusoidal signals. This is where all of our depth information is. But when we solve for that depth information, we have to use the arctangent function. And since the arctangent function is only defined from 0 to 2 pi, we get these sharp discontinuities, which we have to resolve using this third signal. I briefly discussed that earlier, but basically it's just a scaling operation. And using these two, this wrapped phase and this low frequency signal, we're able to generate what's called a stare image, or we'll call it K here. But basically all this is doing is it's saying how many 2 pi's do we have to add to this, this high frequency wrapped phase in order to recover our nice continuous phase. So once we apply this stare map to our high frequency wrapped phase, we're able to get our unwrapped phase. And from our unwrapped phase, we're able to recover our original depth information. And once again, this is a ton of information, but really all this is saying is that from our encoded image that's used, encoded using a variable precision parameter, we're able to recover our depth information if we just apply a little bit of math. So how about some results? So throughout this presentation, I've promised you guys that that where there is a higher frequency within our variable precision parameter, we're going to get less error. That's really what this experiment highlights. We can see that this is the number of encoding periods. So as where the number of this image is lighter, we have a higher distribution of encoding periods. So we have more encoding periods, and where it's darker, we have fewer encoding periods. And that's reflected in our this error map over here. And by the way, reconstruction error is just we've taken what the depth information that we've recovered from our encoded signals, and we're just comparing it to the original information. So where this is lighter, we have more error, which corresponds to where we're using fewer encoding periods. So that's, it's just basically what I promised is actually happening here. So we get less error where we have a higher distribution of encoding periods. So graphically and numerically, it looks a little bit like this. So there are fixed frequency methods, which we're going to compare against. So we have 2 encoding periods and 6 encoding periods, so high frequency and low frequency. And we can see the low frequency method has a lot of error. The higher frequency equivalent has less error. When you use a variable encoding frequency, we're able to get marginally less error, or marginally more error than the higher frequency case, but at the cost of less file size. So here are the associated file sizes, and I'm going to kind of maybe brush through this to get to some of the more interesting results. But this metric here, this 0.31 microns per kilobyte, is the decrease in error that we get when we're going from 2 encoding periods to 6 encoding periods per additional kilobyte of file size associated with that encoded image. But when we compare from the 2 encoding periods in the fixed frequency method to our variable frequency method, I'm able to achieve a greater decrease in error per kilobyte of additional file size. So what that means is that the variable frequency method is kind of the best of both worlds. I get slightly more error, but I get a lot less file size, is really all this metric is reporting. Up to this point, I've talked about distributing our frequency about a normal distribution centered about the mean the mean depth value present in the scene. And that might not always be ideal. So to illustrate that, I'm going to revisit this very high resolution surface scan of Mars. And before I get too into detail about it, I just want to talk about how cool this scan is. Again, like I said, a big space nerd, so any space data is cool to me. But this scan is really, really big. It's 14,000 by 7,000 pixels, and all the examples that I've used previously have a depth range in millimeters. This has a depth range of 730 meters, so it's just huge. It's a huge scan, and it's almost half a gigabyte of data in its raw form. But like we said, we have this region of interest. We have that crater present in that scene. And if I take this data and I encode it using a normal distribution centered about the mean depth value present in the scene, we can see that I'm going to encode the plane with a high number of encoding periods, and I'm going to encode my region of interest with fewer encoding periods. And that's reflected in this error map. So we can see I get higher error in my region of interest, which is not ideal. Even though we're still able to reduce file size, we want to encode our region of interest with higher precision. So I can just flip the distribution. I can invert my normal distribution, and now I'm encoding my region of interest with higher precision. So we're able to get a 0.05 meter RMS error in our region of interest, even though we have a 0.106 meter RMS error globally. And we're able to achieve even greater file size reductions. So we're going from 411 megabytes all the way down to 27 megabytes for this huge scan, while maintaining just incredible resolution in our, not resolution, excuse me, precision in our region of interest. So we've relaxed our precision constraint in regions that we maybe care less about. So another cool example is, we don't even have to use normal distribution. So we've talked about how we can invert our distribution, our normal distribution, if we want to, if we need to, but we could use whatever distribution we want. So also just a brief shout out, this is Jacob Nishimura here to the side, who's one of the authors on this paper, and this is Xiaobing Zhu, who's another student in our lab. But we can see that there's two people present in the scene, and we can't just use a normal distribution because we want to encode both people with high precision, but Xiaobing is taking up more space in the frame because he's closer to the camera. So we can see that more points are associated with Xiaobing and fewer are associated with Jacob. But if we use MATLAB's facial recognition algorithms, we're able to detect where their faces are and then center a bimodal distribution around both people, and we're able to encode our data, and we get very low error where the people are, which is exactly what we want. So what this experiment's illustrated is that we're able to just arbitrarily select our distribution, and we're able to intelligently select points within our scene in order to determine where we center those distributions. So just in summary here, this method has shown a novel way of encoding 3D range geometry within the color channels of a 2D RGB image using a variable frequency parameter, which enables us or allows us to encode things that we care about, regions of interest with higher precision while relaxing global precision constraints such that we can reduce our file size. Additionally, we've shown that we're able to arbitrarily select distributions, and that makes it really an applicable method to a lot of applications because you can really distribute things however you need to fit either your data or that application. That being said, here's some links to the different copies of the paper. If you guys are interested, this is was the version published for the conference in January, and this was over here, this QR code on the right is the version that was published for at Applied Optics in the journal in June of 2020. And here's a link to our lab's website as well if you care to look for more information. But thank you very much.
All right, thanks, Matt. And to keep on schedule, I think we're going to move right along here. And if you have any questions, we will open those back up in the coffee break. So for now, let's move on to our next presenter. And you should have host controls to be able to share your screen. So our next presenter is Xiaowei Hu, and he will be talking to us about large depth of field 3D shape measurement inspired by computational imaging. Xiaowei received his BS in Control Science and Engineering from the University of Electronics Science and Technology in 2015, and he's currently a postdoctorate in the Department of Electronic Engineering from Tsinghua University. So with that, we look forward to your talk, and please take it away.
Excuse me. I just want to remind that in the last 5 minutes, I think the audience can vote for each presenters. Maybe I'm not sure the audience knew this vote or not.
Okay, Professor Wang is talking about how to vote for each speaker, and
yeah,
maybe
in the
you
last
can
5 minutes, I think, right?
Yeah, that's right. And maybe in the coffee break. Okay, so it's my turn to give a talk.
Okay, go ahead.
Okay?
Yeah.
Okay. Is anything running right now? The video, the sound?
It is fine.
Okay, I will. Okay. Good morning, everyone. Thanks for invitation from Professor Zhang, and thanks every professor and volunteer for carefully organization. First, I will give a 5.5-year PhD candidate in the Department of Electronic Engineering of Tsinghua University. My main research includes structured 3D imaging and computational imaging. I'm co-advised by Professor Wang from Tsinghua University and Professor Zhang from Purdue University. For today's talk, I will just talk about the problem, the idea, and share personal perspectives. I will skip the details, so if you want to know detailed techniques, just go to my Google Scholar or ResearchGate or contact with me directly. Today, my talk is about how to realize fast, accurate, and large depths of field structured 3D imaging from the viewpoint of computational imaging. It includes 4 parts: the problem, 2 related works, and the personal perspective. Let's start from the problem. Current 3D structured devices can be classified into 2 types: the consumer and the industrial applications. For consumer applications like Kinect, they can cover very large depth range. They are fast, but they are in a low accuracy. For industrial applications such as GOM auto system, they are in high accuracy, but they can only cover very small depth range. This challenge comes from that due to the limited light source power, large depth variation often requires a big aperture, which brings defocus blur, thus cause low accuracy. This is an example that the near and the far object are out of focus. The corresponding 3D reconstruction result is either in low quality or missed. We can conclude that the current 3D imaging method cannot work well in large depth variation scene. Current methods working on extending the depth range of structured 3D imaging can be classified into 2 types: multi-focusing method and the single focusing method. Multi-focusing method set multiple focal plan and merge results from different focus settings. It can cover very large depth range, but it is slow and complicated. In contrast, single focusing method uses only 1 focal plan. It works on accommodate the blur effect. It's easy and fast, but it can only cover a very small depth range. The first work I will talk about is that to improve the speed of multi-focusing method. Solve the problem, let's find why the mechanical focus changing length is slow. Left is a diagram of human eye, and the right picture is the typical structure of the lens with the soft tissue. While for normal lens, it consists of rigid glasses, and the focus is changed by mechanical moving. Thus, it's slow and unstable. Here we introduced the concept of the electronic tunable lens, or we also call it the liquid lens. Just look at the picture. The lens is made by soft membrane. A change of pressure in the container causes the membrane to deflect. Thus, the lens focus is changed. Bottom left are some liquid lens from Oct.18. It can be used together with the normal lens. We test the speed of the liquid lens by a high-speed camera. The results show that its response of step signal can achieve as fast as 15 milliseconds. Another advantage of liquid lens is it's very stable. It has always been widely used in many fields, like microscopy, laser engineering, or medical imaging. Based on the advantage of the liquid lens, we propose to use the liquid lens in structured 3D imaging. This is our first work, named 3D EDOF by ETL. This is a framework of our proposed method. This system includes a projector, a camera attached with a liquid lens, and a control board. The core idea is to use the liquid lens instead of the mechanical focus changing lens. Let's see the details. For simplicity, we fix the projector focus at 800 meters, which can cover a total depth range. We set the camera focus to 3 different positions by the liquid lens. There are 2 main novelties of our method. The first one is that we can get always in focus illumination imaging using the liquid lens. The second one is that we proposed an efficient phase unwrapping based on the focal length constraint. This is an example of the system. It can be found that the single focusing camera cannot cover the large depth range, but we can change the focus through the liquid lens, and we can get in focus the image of each object in the scene. Here I will give a simple explanation of the second novelty. Different from the traditional method, which project fringing patterns in many different frequencies for each focal distance, we propose to project only one frequency pattern for each focal length setting. This method can save the number of needed patterns by half and improve the reconstruction speed twice. The core idea is shown as here. We propose to unwrap the face by taking advantage of the focal length information. I will show the effectiveness of this method by the real-time experiment. In experiment, we first verify the accuracy of our method by reconstructing the sphere. We placed 3 different sized spheres at 3 different positions respectively. We compare 4 focal plane settings. The first is the camera is focused at 415 millimeters. The second one is at 800 millimeters, and the third one is at the 1300 millimeters, and the last one is ours. We call it as all-in focus method. After obtaining the 3D result, we fit the sphere with the ideal model and calculate the mean error and the root mean square error. The figure shows the reconstruction result and the error map. The table shows the mean error and the root mean square error. Let's take the first sphere, which is placed at the 415 millimeters as example. You can find that if the camera's focus is far away from the sphere's position, the error is getting bigger. However, since our method can get always in focus image, we can always get the high accuracy result in a very large depth range. Next, we keep the same focus length settings unchanged. We replace the sphere with the static studios. From the first row to the third row is a condition that the camera is focused at 3 distance respectively. The last row is our method. Just the same as what we get in the last experiment, we can find that the lens blurry has a huge influence on the reconstructing details. Our method can always generate the finest details from 415 millimeters to 1300 millimeters, which means that our method can effectively extend the working range and keep a very high resolution. Lastly, I will show the real-time reconstruction of the dynamic scene to verify the effectiveness of the proposed face unwrapping method. Figure A. In this experiment, we move the first and the third object respectively. Video A to the video C is the result when camera is focused at different places. And the video D is the result of our method. You can find that the 2D video of our method, that the focus is changed by the liquid lens in very high speed, just shown here. This fully demonstrates that our method, we can use the liquid lens to achieve very high speed focus changing, and we can get the always in focus 3D result compared to the fixed focus condition. So from above experiment, we can conclude that our method can effectively extend the depth of field of high accuracy 3D imaging in 20 Hz. To summarize, we just solved the problem of the multi-focusing method by liquid lens. However, as all of you can imagine, if we increase the number of the focal plane we used, the multi-focusing method will be slow, and fast doesn't mean the high speed. So could we achieve that the 3D imaging ability whose depth range is as deep as multi-focusing method, and whose speed is also as fast as single focusing method? That means that we want both. Yes, we just solved the problem by the liquid lens. This is not the computational imaging. Let's look back and find the fundamental theory of the illumination imaging model. This is the principle of the typical active illumination imaging model. This system includes a light source. The scene reflects the light, the lens collects the light, then the signal is transferred by the emission sensor and after an image. There are lots of simplifications and limitations of this model. For example, due to we use the perspective projection model, the depth Z and the light angle are lost. Color information is generated by Bayer filter. Thus, we lost the spectrum information. Also, we must set some exposure time to get enough light. Thus, the temporal information is also lost. We can find that everything here used in this model is fixed. We already do everything we can based on this model. So different from the traditional illumination imaging model, this is the computational illumination imaging model. In this model, there are many coding and computational optics in the system, such as we can use the coded light source, or we can code the light pace, or we can code the pipe plan, or code the focal plan. And what's the most important? Now the image is not just a simple analog to digital conversion, then we can get the image together with the coded optics. The main advantage of the computational imaging model include two parts. The first one is that it can generate a new imaging functionality, such as extended depth of view, spatial or temporal resolution, and dynamic range. The second one is that it can improve performance to complex ratio, which means you can use the smaller weight or cost to get more functions. Based on this, I will talk about how to solve the previous problem inspired by computational imaging. Just look at the traditional multifocusing model as described above. If we want to cover a large depth range, we need to change focus, then start exposure. Then we change the focus again and do about steps again. You can find that the focus change and the exposure is running separately. Thus, the more focal plan, the slower speed it is. Just imagine that if we change the focal plan at the same time as the exposure, then adjusting focus does not will affect the imaging collecting, and the speed is nothing related to the focus changing. This is the technique we call the focal sweeping model. Just looking at the video, you can find the focus of the lens is changing at the same time as exposure. This is the biggest difference from a traditional model. Except the speed change advantage, there are many advantages of the focal sweeping. The function P here is the point spread function of the normal image. It is fixed and related to the depth Z. The PSF of the focal sweeping is IPSF. You can find that if we give an optimal driving function to the lens focus, we can get a depth-independent IPS. The benefits of the focal sweeping can be summarized as follows. The first one is that since IPSF is independent of the depth, we can use one blur kernel for large depth range. The second one is that there is no segmentation and merging anymore, and no need to do many calibration. Finally, and also the most important one, it is as fast as single focusing, and also as deep as multi-focusing. Yes, now we can get the boss. This is an example of the 2D imaging from the figure A to the figure C. The camera is focused on each resolution chart respectively. Figure D is a raw obtained image from focus sweep, and figure E is a deblurred image of D. It can be found that the deblurred focus sweeping image can obtain always in focus image from near to far. Based on the new focus sweep technique described above, we developed the structured 3D imaging depth of field technique, named 3D EDOF by focus sweep. This is the framework of the proposed method. The main difference between this one and the previous one is that now the liquid lens is driven by continuous wave, not discrete signal. The focal plan is modulated. This idea is inspired by the computational imaging, that is the focal plan coding. And this is the algorithm procedure corresponding to the proposed method. The liquid lens is driven at the same period as the camera and the projector. The obtained binary defocusing patterns are called original focus sweep images. After the focal sweeping deblurring technique is applied, the all-in-focus patterns can be generated. Afterwards, they are used for 3D reconstruction. To validate the algorithm, we developed a system as shown here. The system consists of one camera equipped with an liquid lens, one projector, and one control board. 3 objects are placed at 3 different distances respectively. First, we analyze the accuracy of the proposed method. We place one sphere at 3 distances respectively. From first to the fourth column show the raw image and the blurred image, the webbed face, the 3D results respectively. The last 2 columns compare our method's error with the condition that the camera's fixed focus at 450 millimeters. It can be found that our method can get always the same error distribution map as the fixed focus condition. But when the sphere is placed far away from the focal plane, we can still get a very high quality result. This experiment fully demonstrates that our method can achieve high accuracy 3D reconstruction. Next, we keep the settings unchanged and replace the sphere with a stereo. Similarly, we compare our method with the fixed focus condition. Just like the above conclusion, you can find that if the object is in focus, our method can get the same result. But when the object is out of focus, typically you see the condition when the stereo is placed at 1200 millimeters, our method can still get a very high accuracy, very fine details. Next, we further perform the multi-objects experiment. Here we compare the condition that the focus fixed at 450 millimeters and 1200 millimeters respectively. You can find that our method can get fine details from the very close bottle cap to the very far, very big stereo. This experiment fully demonstrated that our method can achieve large depth range 3D reconstruction. And finally, we made a dynamically moving and shape-changing hand. Please look at this video. This video is running at 33 Hz. In conclusion, through the focus sweeping technique, we can achieve high accuracy, large depth range 3D reconstruction at a resolution of 512 by 512 and a frame rate of 33 Hz. This opens a new view for the future work. From about the two work, we already appreciate the beauty of the computational imaging. Next, I will share some of the personal perspective on this field. My concern is that for structured 3D imaging, where are we now and what the future looks like? There are 2 questions. The first one is that how to break the trade-off among the speed, the accuracy, and the measurement volume. There is always a trade-off. The second one is that how could this technique survive under the poor conditions, like the strong sunlight, the specular surface, and the transparent object and the interreflecting object? My personal idea is that maybe we can look inside and explore new illumination imaging functionalities. This is not the way to the answer, but it is a new start point. Okay, that's all my sharing. Thank you all for listening. If you want to know me more, please search my Google Scholar or ResearchGate, or download our recent paper related to these works. Thank you all again. Okay, that's all my sharing.
Thank you very much. This seems like very great work to extend the depth range. Oh, go ahead, sorry.
Finally, last word, me. Thank you.
Thank you for this great talk. Please remember, if you're in the audience, to scan the QR code if you'd like to register a vote. That's the voting mechanism that we'll be using. And to keep on task here, let's go ahead and go to our last presenter of this first part of the session. So our last presenter today in this first half, I just lost my slide here. Is Chuan Deng. Chuan is a postgraduate student with the Department of Optoelectronic Engineering at Jinan University. Her research interests are optical imaging, single pixel imaging, and image-free object tracking. Chuan is going to be talking to us today about image-free, real-time, fast-moving object 3D tracking with single pixel detectors. So it seems you are ready, and the floor is yours whenever you are.
Hi, hello everybody. Can you hear me?
Yes.
Okay, thank you. Okay, let's start. Okay. Good morning, ladies and gentlemen. I'm Deng Qiwen from Jinan University, Guangzhou, China. My presentation is image-free, real-time, fast-moving object 3D checking with single pixel detectors. My presentation is organized as follows. First, I will give a brief introduction about fast-moving object 3D checking. Real-time 3D checking for fast-moving object has found various applications in different fields, such as missile checking in defense, cells or particles checking in biomedicine, self-driving cars in transportation, and eagle eye system in sports. There have been numerous methods proposed for moving object 3D checking. Image-based approaches are widely used. They generally consist of two steps. First, a sequence of images is captured. Second, the position of the target object is extracted from the captured images through image post-processing, including object detection, background removal, and trajectory estimation. Image-based systems are applicable for object checking in multiple scales, from micro or nano objects to common-sized objects, and even to astronomical objects. However, fast-moving object checking is a challenge for image-based object checking methods. On one hand, motion blur caused by high-speed motion of the target object affects the image quality. It results in errors in object checking. In order to reduce motion blur, reducing the exposure time will lead to a low signal-to-noise ratio of image captured, which also affects the image quality. On the other hand, although high-speed photography enables fast-moving object checking continuously in a high frame rate, it is difficult to apply high-speed photography for a long duration. It is because a high-speed camera generates a huge number of data in a short time. But the bandwidth of data transfer and the capacity of data storage is limited. In addition, real-time object checking is also difficult. It is because the advanced image post-processing and analysis algorithms are generally computation exhaustive. A long computation time results in the difficulty in real-time object checking. In a word, real-time and long-duration object checking remains a challenge. Recalling that 3D object checking is a problem to solve 3 spatial coordinates, that is X, Y, and Z. So it is rather resource wasting to obtain 3 values by acquiring millions of image pixels. Our idea is to reduce such redundancy to achieve efficient spatial information acquisition. Here, we propose an image-free method for fast-moving object 3D checking. The method is able to calculate the position of the object through spatial light modulation and single pixel detection. More importantly, the proposed method needs no image acquisition and analysis. What's more, the method also removes the need of any image sensors. It uses only 2 cost-effective photodetectors instead. To derive the position of the objects, the method only needs 12 intensity values for each position computation. In conclusion, the proposed method is not only data efficient, but also computation efficient. It allows for real-time and long-duration object checking. Mathematically, a 3D position can be synthesized by 2 2D projection positions in 2 orthogonal planes. Therefore, the key of our approach is to derive the position of the objects in 2 orthogonal projection planes. So, how can we calculate the 2D projection positions? As we can see, this is the target object in a 3D space. The position of the object in projection plane X, O, Z is X0 and Z0. To derive such a position, we propose to use 2 sets of 3-step phase-shifting Fourier basis patterns for spatial light modulation. The first set of patterns is used to encode the spatial information in X direction, and the latter for Z direction. By illuminating the target objects with these patterns sequentially through a spatial light modulator, we can encode the spatial coordinates into 6 intensities. The resulting light intensities are measured by a photodetector, such as photodiode, solar cells, or photomultiplier tube. With the 6 intensities, we can calculate the position of the object through these 2 simple equations. It demonstrates the advantages of data and computation efficiency of the proposed method. By looping the 6 patterns, we can continuously calculate the 2D position of the object in the projection plane. Similarly, we can check the object in projection plane Y, O, Z by illuminating the patterns from directions which is orthogonal to the plane. But it turns out doubling the cost. In particular, it seems we have to use two spatial light modulators. Here, we propose to a setup which is able to achieve 3D object checking with only one spatial light modulator. The key is the beam splitter. It can split the light beam generated by the modulator into two and direct them to the target object from two orthogonal directions simultaneously. The resulting light beams passing through the objects are collected by two photodetectors. The intensity values corresponding to each photodetector are decoded to solve the 2D projection positions and synthesize the 3D checking results. In this proof of concept experiment, we simulate a fast-moving object using a metallic hollow ball. The ball is threaded by a helical wire. When the ball is released, it goes down along the wire due to the gravity. We record the intensity values from the two photodetectors and the reconstructed 3D trajectory in the video. The video will be playing in normal speed. This is our checking results. As the video shows, the ball moves in a high speed and it leaves the scene in a short time. We also slow down the video by a factor of 50. The figure on the right is the 3D checking results. The red point denotes to the current position, and the gray line relates to the historical chase. They are synthesized by green and blue curves in projection plane XOZ and YOZ. The windows on the left are the intensity values collected by the two photodetectors. Note that the yellow curves denotes to the average intensity value for each 6 patterns. As the result shows, the reconstructed 3D trajectory coincides with the real helical wire, which validates the checking results. Here are the average intensity values collected by the two photodetectors during the entire checking process. As we can see, the measurements are invariant with time in the first and last periods. It is because the target object not exists in the scene. Once the target object enters and moves in the scene, the measurements fluctuate sharply. From what is mentioned above, the proposed method is capable of moving object detection. According to the stationarity of the measurements. What's more, the proposed method is also able to measure the speed of the objects. The checking frame rate of our experiment is 1,666 frames per second, as using a 10,000 Hertz spatial light modulator, and each position calculation takes 6 patterns. Therefore, the motion of the object lasts for 0.45 seconds, and the average speed measured is 0.37 per second. In summary, we present an image-free approach, allowing for real-time and long-duration object checking. The proposed method effectively acquires spatial information through spatial light modulation and single pixel detection. What's more, the proposed method is cost-effective, data and computation efficient. It reduces the captured data by a factor of million, and the processing time is less than a microsecond for each position calculation. Also, the checking results achieve a 1,666 checking frame rate using a spatial light modulator, operates at refreshing rate of 10,000 Hertz. Given the advantages of wide working spectral range by photodetector, it is potentially applicable for invisible object checking. Finally, I'd like to thank everyone who has helped me in these projects. Thank you.
Thank you very much for your great presentation. I will ask if there are any questions at this time.
Yeah.
Did we have any questions come in from Bilibili or YouTube? All right, so I will ask a question. What did you find or what do you think with the results you have so far might be the limitations of this method? So you have 1,600 about tracking frames per second, and you showed that really cool experiment of the ball falling down the wire. What are the upper limits of this method? What's next for this approach?
What's the next? I'm sorry, could you repeat it again?
Yeah, I'm just curious about the next future work for this approach or other samples that you may wish to track at faster rates than I think 0.4 meters per second.
The future work of our approach is to extend the method for to multiple object checking, because our method is achieve single object checking in current stage.
Yeah, that would be really exciting. We look forward to seeing it. So with that, I think we are at our coffee break, and we will reconvene in approximately 7 minutes. So thank you all.
Okay, thank you.
And if there's any questions from the first two presentations, we can open that back up now as well, or for any of the 3 presentations so far.
My research will include the 3D imaging and some pattern recognition. So for the time, we will start the second half session soon. The first presenter is the Chenzhuo Li from Beihang University. Chenzhuo, are you okay? Are you ready now?
Yes, I'm ready.
Yeah. Chenzhuo Li currently is the PhD student in the School of Aeronautic Science and Engineering at Beihang University. His research interests include digital image coloration and fluorescent imaging. So, Chenzhuo, please start your presentation.
Yeah, thank you. Good morning and good evening, everyone. My name is Li Chenzhuo. I'm a PhD student from Beihang University. I'm now working on digital image correlation under Professor Pan Bing. The topic for today's presentation is new exploration and application of fluorescent digital image correlation. Okay, let's start with the presentation. So here is the outline of my talk. I will start with a short introduction, talking about the problems existing in current DIC measurements. Then I will introduce the fluorescent digital image correlation and the advantages it could bring to macro-scale DIC measurement. After that, I will be showing some of the experiments we conducted to check these distinct advantages and some applications we conducted recently using the fluorescent DIC. And then I will give some concluding remarks. Okay, for those who have used the DIC to measure the displacement or the stream, it will be very clear that the implementation of DIC generally contains 3 steps: speckle fabrication, image acquisition, and image analyze. So for test objects without natural surface textures, speckle pattern fabrication is an essential and important procedure in DIC measurements. The accuracy and precision of DIC measurements also rely heavily on the quality of the decorated speckle patterns. In DIC community, the most popular method of speckle pattern fabrication is spraying black and white paints on a specimen surface by operating a spray bottle or airbrush. Because the reflectivity of the black paint is quite different from the white paint, the method can easily fabricate speckle patterns with high contrast. But this simple method has some problems in practical use. First, the smooth surfaces of the specimen or the speckle can lead to specular reflections, which can result in uneven distribution of image grayscales or the local area overexposure. So the shape and deformation of some regions can hardly be measured. Second, the reflectivity of the black paint is much smaller than that of the white paint, but it is not negligibly small. So the contrast of the speckle pattern cannot reach a very high level, which can further affect the measurement accuracy and precision. Third, the use of reflection-based speckles will cover the specimen surfaces during DIC measurement. So the evolution of surface textures of opaque specimen or the internal structures of transparent specimen and the mechanical behaviors cannot be observed during the measurement. To solve these problems, we applied fluorescent ink for macro-scale speckle pattern fabrication and explored its advantages and applications in macro-scale DIC measurement. Fluorescent DIC was first proposed and developed widely in micro-scale measurement. The principle of fluorescence is simple. Fluorescent speckles absorb a range of wavelengths of light and emit other wavelengths of light. By using a bandpass filter, only the emitting light enters the camera to form a speckle image. So In macro-scale DIC measurement, if we spray fluorescent ink to fabricate the speckle pattern, the aforementioned problems can be solved. First, because the wavelengths of the light emission and the light excitation doesn't overlap, the specular reflection can be readily avoided by the idea of active imaging and implemented by equipping bandpass filters. Second, when capturing the fluorescent speckle patterns, there is almost no light reflected or emitted from the background. Therefore, the contrast of the acquired speckle pattern is obviously higher than that of the conventional ones. Third, since some fluorescent paint has transparent appearance, it will not block the decorated specimen. So the evolution of internal structures and the mechanical behaviors of transparent or semi-transparent specimens can be simultaneously observed by using an additional imaging system. Okay, let's move on to the experiments. The first experiment we conducted is to measure the shape and the diameter of a metal ball using the classic DIC, the cross-polarized DIC, and our fluorescent DIC. To guarantee the same speckle distribution for all three systems, we mixed the titanium dioxide particles and the fluorescent ink. The mixture has both fluorescent and reflective features. Before measurement, the mixture was sprayed on the surface of the ball. Here are the images captured by the three systems and the calculated profiles. As can be seen from the classic 3D DIC result, due to the specular reflections on the spherical surface, a large portion of the specified ROI fails to reconstruct. The result derived from the cross-polarized 3D DIC system seems much better, but reconstruction failure still exists because the very intense specular reflections are beyond the capability of the polarizers, whose extinction ratio is insufficient for suppression. Additionally, the use of polarizers complicates the system, and the cross-polarization adjustment can be cumbersome. In practical use, a slight deviation from the orthogonality of the polarizers can sharply decrease the capability of the specular reflection elimination. By comparison, it can be seen from the fluorescent 3D DIC result that the fluorescent system is not affected by the specular reflection, and the 3D profile of the ROI is fully reconstructed, where the estimated diameter error is least. This experiment validates the effectiveness of using fluorescent DIC to eliminate the specular reflection. To show the high quality of the fluorescent speckle pattern in DIC measurements, we analyzed the speckle images and conducted the in-plane and out-of-plane translation tests. The speckles were fabricated on a black plate using the same fluorescent reflective speckles to maintain the same speckle distribution. From the captured images, it can be seen that the contrast of the images captured by the classic system is lower than the fluorescent system. And this is also verified by the gap in the histogram distribution widths. The mean intensity gradient and the optimum subset size calculated from the two speckle images also indicate that fluorescent speckle image has more abundant features and higher quality. From the translation test, the average error and the standard deviation of fluorescent DIC are better than the classic DIC. Therefore, we concluded that the fluorescent DIC systems can capture higher quality speckle images and promote the DIC measurement accuracy and precision. So here is a uniaxial tensile test we conducted on a composite material specimen made of transparent FEP pipe and ringed e-gloss fiber multifilament. During the experiment, a set of red imaging system and a set of blue imaging system were used for simultaneous surface stream measurement and internal structure monitoring. The speckle decorated on the pipe surface was pure fluorescent ink. It can be seen that the red channel captured clear images of the internal structure of the glass fiber, and the blue channel captured the high contrast surface speckle patterns. By using 2D DLSA algorithm, the tensile strain can be derived, and the stress strain curve with the internal structures states is plotted on the right side. From experimental result, 2 elastic stages, stage 1 and stage 2, and 2 plastic plateaus are observed. In stage 1, the internal glass fiber is slack, and the increased loading is carried totally by the pipe, where the effective Young's modulus of the specimen is equal to 202 megapascals. Along with the strain increase, the pipe enters the first plastic plateau, and the internal glass fiber becomes gradually tight until the specimen enters the second elastic stage. In stage 2, the glass fiber begins to bear the tensile load. The stress increases linearly with the applied strain, and finally reaches the ultimate tensile strength, followed by the filament break and the new plastic plateau. Here we noticed that the stress level of this plateau is higher than the first one, because it presents not only the plastic behavior of the pipe, but also the fractional interaction of the glass fiber. This experiment proves that the internal structures of transparent specimens are observable once using fluorescent speckles in DLSA measurements. This improvement is expected to assist researchers to better understand the mechanical property evolution of specimens with complex structures. Here is our most recent application of fluorescent DIC. It is a direct application of using fluorescent DIC to eliminate the specular reflection. We implemented the fluorescent DIC with the combined use of built-in ultraviolet coaxial illumination and fluorescent telecentric imaging. This 2D DIC system is very compact and suitable for measurement in small spaces. The improved 2D DIC system first excites the fluorescent speckles on the surface, and using the ultraviolet light source through the built-in coaxial illumination, and then employs a monochromatic telecentric imaging system to capture the images of the excited speckles. By tracking the movement of fluorescent speckles using DIC, full field displacements and strings can be retrieved. To demonstrate the superiority of this proposed technique, we evaluated and compared the quality of speckle images captured by using our previously proposed advanced 2D DIC, the advanced 2D DIC with built-in blue coaxial illumination, and the advanced 2D DIC with both built-in ultraviolet coaxial illumination and fluorescent imaging. From the image captured by the advanced 2D DIC system, we can see that the grayscale distribution width reaches only 84, representing the insufficient contrast of the speckle image. The factors that affect the quality of the speckle image are of two aspects. First, the local overexposure caused by specular reflection of the smooth speckle surface. Second, the light reflected from the black background is not negligibly small. From the image acquired by the advanced 2D DIC system with built-in black coaxial illumination, we discovered that the contrast of the speckle image is sharply decreased. This is because using built-in coaxial illumination can only compact the measuring system and optimize its lighting mode, but cannot improve the quality of the acquired speckle images. Instead, the speckle reflection of the imaging lenses can even severely reduce the image quality. From the image acquired by our proposed technique, we found that the contrast of the speckle image is obviously improved because the factors that affect the imaging quality have been effectively addressed after employing fluorescent imaging. Here, we also used the mean intensity gradient to evaluate the quality of the speckle images and found that the proposed technique has the highest MIG value. So this application of fluorescent DIC is effective and successful. So the conclusion is that we have explored the advantages and applications of fluorescent DIC in macroscale deformation measurement. It can eliminate the specular reflection caused by the spaceman surface or the speckle, and it can enhance the speckle pattern contrast due to its photoilluminance feature. It can also enrich the measurement functions using its transparent appearance without complicating the measurement system or introducing additional problems. The first advantage can also be used to eliminate the specular reflection of optical components in coaxial illumination. Then the fluorescent telecentric imaging can be combined with built-in ultraviolet coaxial illumination to conduct DIC measurement in small spaces. To show the enriched measurement functions, we realized the simultaneous measurement of superficial strain and the observation of internal structures. Besides these applications, we can also use fluorescent DIC to overcome the specular reflection of observed windows or integrate multiple chromatic fluorescent speckles and corresponding imaging systems to realize multi-surface displacement and stream measurement, and even out-of-plane stream measurement. Okay, thank you very much for everybody's time and attention. Thank you.
Thanks for Chen Zuo's presentation. Any questions? If no questions, let's move on to the second presenter. The second presenter is Yunfan Wang, also from the Beihang University, a School of Instrumentation and Optoelectronic Engineering. Yunfan, are you ready? Yeah, so Yunfan Wang received his bachelor degree in measurement and control technology and instrument from the Beihang University, and he is currently a PhD student in the School of Instrumentation and Optoelectronic Engineering. He is a SPIE student member. His research interests including 3D measurement and computational photography. So, Yunfan, please start your presentation. You could open your microphone. We cannot hear from you. Yeah.
Yeah. Can you hear me?
Okay.
Okay. Right. So good morning, good afternoon, good evening. Depends on where you are. Also, thanks Professor Wang and Professor Bell, and also thanks Professor Zhang for invitation. I'm Yunfan, a PhD student from Beihang University, and today I'd like to share some of the recent research in our group about the application of point square function for fringe projection profilometry. Here's the content. I will first go with the motivation and then the basic PSF calibration method. After that, I will introduce a typical application for binary defocusing technique and also cover the recent research in our group about spatially wiring PSF acquisition. So the motivation. The fringe projection profilometry is still a triangulation-based method. A series of fringe patterns are projected onto the object and the encoded phase information is used to find the matching point. The accuracy is highly dependent on the point-to-point relationship. However, any system has its limited depth of field. It will be fine if the object is within the scope, but when it comes to the large workpiece, especially with large depth variation, the point-to-point relationship will be affected, and the near side is clear, but the far side is blurred. This defocus will inevitably cause the loss of accuracy. And I think Mr. Hu has already introduced this effect. Actually, different imaging region has different defocusing effect. And here is an example. You can see that the shape of peripheral blur is quite different from the central one. That is because the optical system is imperfect. In imaging science, there are 5 aberrations affecting the imaging quality, but for most of the system calibration, only the geometrical distortion is calibrated. But in fact, all the aberration will affect the phase information. For small defocusing or nearly focus, the error from aberrations is relatively small, so the blur is usually approximated as Gaussian function. It has no zero, so it won't severely influence the phase matching. And theoretically, for the sinusoidal pattern, it will only reduce the modulation. Well, for the binary fringe, it can even help to generate the pseudo-sinusoidal pattern for high-speed measurement. However, the Gaussian approximation is not always accurate. When it comes to the large defocus, the blur is quite complex, since the aberration effect will be enlarged. And here is a pattern with astigmatism. You can see the modulation is quite uneven. And here is another example of projector defocusing. You can see that while defocus increasing, the fringe even inverted. And please notice that this is a static fringe pattern, and I only changed the focusing distance. I didn't display the phase shifting pattern. Since the unwanted defocusing will severely affect the fringe quality, it's naturally to a question how to manipulate this defocus effect. And we propose using point spread function calibration to solve this problem. Well, the point spread function describes the response of an imaging system to a point source or point object, and it can be used to quantitatively estimate the defocusing effect. And this technique has been widely used in computer vision or computer graphics community for extending the depth of field or super resolution. But there are only limited research for fringe projection method. As for the fringe projection instrument, one of the possible applications is to use the calibration result to simulate different conditions and then use the simulation to find the optimized parameters. The simplest way for PSF calibration is point source method. We use the projector to display a dot metric pattern. The recorded blur is the sampled PSF. And this procedure can be repeated at different distance, and then the PSF at different depths can be obtained. And also, through geometrical optics, we can further establish the relationship between the size of PSF and the focusing distance. And by doing so, the mapping allows us to manipulate the defocus directly by the distance. And here is the formula. Since most of the coefficients are constant, it can be simplified. So only 3 coefficients need to be calibrated. And here is the experimental projector focusing. You can see that with focus changing, the PSF varies significantly. And here is the fitting curve. You can see that mapping between focusing distance and PSF size can be calibrated precisely. Well, in the last part, I introduced a simple PSF calibration method, but how to use this calibration for fringe projection profilometry? Well, one of the applications for PSF is the parameter optimization for binary defocusing system. Well, in such system, the fringe pattern is generated through optical defocusing. The input is a binary pattern, but after optical low-pass filtering, a pseudo-sinusoidal pattern can be obtained. So in order to get high quality fringe pattern, we need to ensure the Gaussian filtering process. So normally this method contains two requirements. One is small fringe period, and the other is small defocusing. This technique is sensitive to the defocus degree. So in order to achieve better performance, we need to manipulate the focus carefully. So the problem is, for the input fringe period t, what is the best focusing distance s to make it properly defocus? And here's the thing. We can first calibrate the physical PSF of the system and then use its priors to simulate different parameter combinations. Then the optimized result can be found according to this simulation. Well, for square binary technique, the best parameters can be clearly analyzed in frequency domain. And both the pattern and PSF has analytic expression. The PSF is Gaussian, and only the unwanted harmonics need to be filtered out. And here is the Fourier transform of square wave and Gaussian function. Then put it together, we can get the expression of the filtered result. And actually, it can be separated into two parts. One is the sinusoidal term, which we want, and the other is harmonics residues, which need to be filtered out. And once we have the fringes and the actual filter kernel, building an objective function for optimization is necessary. And here we define the single point sinusoidal error for to describe the intensity residues between ideal sign function and filtered function, pattern after phase shifting. From the previous Fourier analysis, it's easy to know that this error contains two parts, and one is the harmonics residues and the other is the noises. Well, furthermore, in order to illustrate the system sensitivity, we add normalized fringe period and also the modulation. Well, this formula is proportional to the phase error actually, and put all the formula together, we get the final objective function. Please note that this term is obtained from PSF calibration. Well, the formula seems horrible, but fortunately, it's a convex function, as shown in the figure. And here is the intersection of the surface. As shown in this figure, given the fringe period t, you can find the minimum, which indicate the appropriate defocusing degree. And here are the experiment results. You can see that different parameters can generate different quality. If the binary fringe is not properly defocused, there will be increased error and severe layered reconstruction. And from the table, we can also see that the simulation predicts the best parameter accurately. The least RMSE occurs when it's come to the least single point sinusoidal error, which means we can use this model to find appropriate parameters. And here is another object. You can see that if the object steps exceeds the sensor steps of field, where the near side is perfectly defocused, but far side remains binary, the reconstruction would be severely affected. And in contrast, through our method, we can find the appropriate parameters to ensure the complicity of the measurement. Well, in binary defocusing technique, we still use Gaussian approximation and shift invariant model since it's simple to analyze and easy to implement. But as I said in motivation, the PSF is really complicated. The more accurate PSF we can obtain, the more accurate analysis we can achieve. So we introduce the spatially varying model. Well, for most of the image processing, the filtering is shift invariant. That is using a single kernel and convolution to get the filtered result. However, in imaging science, this process should be the integral of different PSFs. In point source method, there are two limitations. One is the Gaussian approximation isn't always applicable due to the imperfection of imaging system. The other is the ISNR of point source method is usually low, which means it's hard to obtain the precise kernel. So apparently, we need a new tool to detect this kernel. Well, the recent work in our group shows that single pixel imaging algorithm can be transplanted into the projector camera system, which helps to increase the accuracy and SNR of PSF measurement. Well, in single pixel imaging, a set of base patterns are projected onto the object, but only one single photodetector is used to collect the signal. But the full image can still be reconstructed through optimization or inverse transform. Well, if we regard the camera sensor as an array of photodetectors, it is possible to know what each pixel sees. Then we can use this technique to acquire the PSF of each pixel with high SNR. And here is an example of camera PSF measurement based on Fourier single pixel imaging. We use a high-res LCD screen to display the periodical base patterns in order to let every pixel can be regarded as single pixel imaging process. Well, the camera response expressed like this, and put all the camera response of different frequency together in frequency domain, and then apply the inverse Fourier transform. The PSF can be obtained. Please note that the PSF should be the one point source to multiple pixel responses. However, in single pixel imaging, what we obtain is the mapping from one pixel to multiple object points. So after inverse Fourier transform, we need to redistribute the coefficient to form the correct mapping. And similar to point source method, we can measure the PSF at different depths by moving the LCD screen, and the interval can be interpolated based on the coordinate transformation. And accordingly, we can acquire the PSF at different depths. And here are some experiment results. The focusing distance is 359 millimeter, where the size of PSF is minimum. And you can also see that as the depth changes, the PSFs of camera varies significantly. And even at the same depth, the shape of peripheral PSF is quite bizarre. And that is because for most lenses, the largest aberration usually occurs on the periphery. This effect can be caused by coma or other aberration. Well, to test the correctness of the reconstructed PSF, we added more experiments on image degradation and image restoration. The first row is image degradation or the blur simulation, and the second row is image restoration. We also compare the simulation result between the point source method and our proposed method. Well, the correlation coefficient shows that it can achieve better accuracy to simulate the physical imaging process. So, well, in conclusion, the undesired defocus will influence the accuracy of fringe projection profilometry, and we propose using PSF calibration to control it quantitatively. Well, for binary defocusing technique, the calibration result can be helpful to find the best parameters through simulation, and by transplanting the single pixel imaging algorithm into traditional projector camera system, the spatially wired PSF at any depth can be measured with high SNR and high accuracy. Well, as for the future, the PSF provides useful information for fringe projection technique, and in the future, more applications such as depth extension, shape from defocus, uncertainty analysis can be investigated, and we are still working on it. And also in this talk, I have omitted some of the mathematical details and theoretical details due to the limited time, but if you are interested in our work, please review these references. Well, that's all. Thank you. And if you have any question, I'd like to answer.
Yeah, any questions? So I just one question. Do you have some, explanation of, limitation of your method?
I think one of the limitation is the calibration process. I mean, you need to pre-calibrate the instrument before you're using it. So it definitely will take some time to finish it. Well, as for the single pixel imaging method to measure the PSF, it will take about 4 minutes to acquire the image in order to reconstruct the PSF. And so if you the measuring scope is really large, so it definitely takes a while to measure the whole range. But we are still working on it to speed up the whole process by some parallel computing or other method to finish it.
I mean, if the calibration is ready, so when the system is used in the outdoor scenario, it is any different or not?
You mean the PSF different or?
Oh, I mean the performance.
Of the
If the performance, if it is used in different scenario.
Well, I think the performance is it depends on the instrument itself. I mean, if you use some global illumination technique into the fringe projection profilometry, so it will be fine. But I mean, our work is just to calibrate the measuring scope. So it's nothing to do with the algorithm you use or the additional processing you use. We just determine the best parameters and determine the defocus. So actually, it's nothing to do with the experiment. PSF is only relative to the optical system.
Okay. Thanks, Winfan's presentation. Thank you.
Okay, thank you.
Yeah, let's move to the third and also our last presenter, Boyang Zhang. Boyang, are you ready, Boyang?
Oh, yes.
Okay.
Can you hear me?
Yeah, sure.
Okay.
Boyang also joined the optical measuring and the inspection lab of Auckland University in 2015. He is now a PhD candidate in the lab. His research interests include optical metrology, photomechanism, optical non-destructive testing, etc., using advanced optical techniques such as digital holography, digital stereography, digital image correlation, etc. Yeah, Boyang, please start your presentation.
Okay, thank you. Okay, hello everyone. My name is Zhang Boyang from the Optical Lab of Auckland University. My advisor is Dr. Yang Lianxiang. Okay, so most of the speakers is discussing the technique about 3D contour measurement or the digital image correlation. But I would like to introduce something different today. It's the NDT method to measure the deformation gradients. So my topic is the spatial phase shift stereography for NDT, potential and limitation. Okay, I will present my topic in 3 parts. First, I will introduce some basic knowledge of the stereography. Then, the 2 major spatial phase shift approaches will be expressed here. And I want to discuss the potential and the limitation of this technique at the end. Okay, let's begin. First is introductions. Composite materials has been widely used in aerospace. And on the left 2 pictures, there are the 2 latest Boeing airplanes, Boeing 777 and 787. If we just look at these 2 airplanes, we can find that the composites used in 777 is only about 20%, but it grows up to 50% in 787. What it means, the composite is becoming the core material in the industry. Okay, not just in airplane. In addition, like the picture showing here, the Formula the F1 Formula racing cars, space shuttles, virus fighters, all using composites as their structure materials. And at the meantime, ASNT already admits that chirography is one of the most effective NDT methods for composite materials inspection. Okay, so the question is, what is chirography and why we choose it? Digital chirography is an optical measurement technique for non-destructive testing and quality control applications, commonly used on composites and metallic materials. It has advantages of eco-friendly, full-field, high-sensitive, non-destructive, and robust. The picture showing here is a commercial chirograph system. It is used to measure the panel on a car. Here, I want to show some applications of the chirography. This one is a vacuum stress chirography system used for the rocket tank inspections. And next, it is a chirography used for the Airbus body inspections. And on the right side corner here, it's a defect detected by the chirograph system. Okay, please allow me to introduce some basic theory of the chirography. By talking chirography, we need to mention the holography first. Holography and chirography both are speckle pattern interferometry technique. They are laser technique. Holography measures the surface deformation by the interference of the reflection light and the reference light here. But chirography measures the relative displacement of the adjacent 2 points by a shearing device. So here is the micros and interferometers. And from the picture here, we can see the defect is hidden under the surface. When we give the loadings, the surface expands, and we capture the image from the first state and the second state. We do the subtractions. For the hologram, we can see a shape like that. And for the chirogram, we can get its first derivation gradients, like the butterfly pattern. Okay, so chirograph system has 2 modes. One is called the intensity mode. Intensity mode has advantages of the real-time inspections. However, we can check the map here. We can find that counting fringes is the only way to do the quantitative analysis. It makes the intensity relatively poor sensitivity. In opposite, by applying some phase shift method, the phase mode has a better contrast and higher sensitivity. Talking about the phase mode, we need to know the phase shift method. There are 2 major phase shift methods. As the intensity formula showing here, that we have 3 unknown parameters here, I, gamma, and theta. Theta is the phase, and the delta is the phase difference, which is directly related to the deformation gradients we want to know. So in these equations, we have 3 unknowns. To solve the phase delta, we need 3 equations with the same parameters, which requires 3 images to solve a single phase. And the schematics showing here, it uses the 4 images. And this method is the most popular algorithms because of the easy calculation. The characteristic of the temporal phase shift method makes it suitable for static measurement because each state you need multiple images. While the spatial phase shift method, it can solve the phase by a single image. It enables the dynamic measurement. And now we're gonna go to the topic, the development of the spatial phase chirography. Okay, now the first method is called the multi-channel method. The idea of this method comes from the temporal phase shift method. We know that it requires at least 3 images to solve the phase value theta. So can we turn the images to the pixels on the single picture? The major theory of this method is that the adjacent pixels can be used to calculate the phase according to the regular phase shift algorithms by applying proper shearing angle. As the picture showing here, the 2 waves have an interference the red one and blue one, with a specific phase difference on the adjacent pixels due to the space angle here. Each pixel can be represented by an intensity equation. Our goal is to solve the phase by adjacent pixels. The first step is to make sure these pixels have the same parameters of the I, gamma, and theta. It requires us to control the aperture size and focal length. In the application, a speckle pattern are required to cover 3 pixels on 3-step method, and cover 4 pixels in 4-step method. The formula here is the 4-step method. And in the 4-step method, we can see the adjacent pixels requires 90 degrees phase difference. So the I1 to I4 represent the pixel 1 to the pixel 4 here. However, the original multi-channel method has 2 limitations. First, in order to achieve a specific phase difference, it is required to adjust to a specific shearing angle precisely, which is not good for application. The second issue is it's a poor spatial resolution because we find we use multi-pixels are required to solve a single phase value. So it's waste a lot of pixels value. And it is proposed applying 5-step arbitrary phase shift method to solve the first issue. As the formula showing here, this algorithm only requires each adjacent pixels has the same phase difference, but not require the specific phase value. It frees the adjusting of the shearing distance, makes the testing more flexible. However, speckle patterns are required to cover 5 pixels, which results in worse spatial resolution. So how to improve the spatial resolution? A 2+2 method is in starting now. We know that shearogram is created by the subtraction of the phase on the different loading state. In these equations, I1 and I2 represent the 2 pixels on the loading state 1, while I1 prime and I2 prime represent the same pixels on the loading state 2. Delta is the phase difference. Here, these 4 equations we can find the 4 unknown parameters can be solved by the 4 equations. But this method has the assumption that I and R are the same on the 2 loading states. That's the reason why this method is still in starting. It still have the problem to solve. In addition, studies have found that speckle patterns could overlap. That's a good news. Compared with original arrangement, calculates the phase by the 1, 2, 3, 4 pixels, then next one's 5, 6, 7, 8. If the speckles can overlap, we can solve the phase by 1, 2, 3, 4, then 2, 3, 4, 5. So we can use all the pixels. It's going to highly improve the spatial resolution. But this method will bring a lot of noise. So it's also in starting now. In general, multi-channel method has advantages of fast calculation, simple setup. It has a large space to develop. Now, please allow me to introduce another more natural spatial phase shift method. It is called the spatial carrier method. The method is first proposed by the Plenary in 1996 from the Institute of the Technical Optics, University of Stuttgart. He used a Mach-Zehnder interferometers plus a Fourier transform to build the first spatial carrier shearography system. And by tilting the mirror 3 in the schematics here, we can generate the shearing. And also, it introduces the carrier frequency f in the formula here, the f0. Carrier frequency is directly related to the shearing angle and the wavelength. After doing the Fourier transform of the light here, on the speckle pattern, the image is transferred to a spectrum on the Fourier domain. The two parts of the spectrum that contain the phase information of recorded shearogram are also separated. The phase differences can be calculated from the complex amplitude by applying a proper selected window inverse Fourier transform. Okay, let's check some schematics on the Fourier domain. Here, on the first schematics, U2 have the carrier frequency f0. When we go to the Fourier domain, the spectrum contains the useful information is light around the f0 in the positive and the negative axis. The real spectrum is shown on the right side. And we can see on the left side and the right side are the useful spectrum. We can create a border to cover these two parts and do the windows in reverse Fourier transform. We can extract the phase information. The original setup of the Plenary has two problems. First, Mach-Zehnder interferometer has too many optical components and a relatively long optical path, which reduces the stability of the system. Second, the size of the beam splitter restricts the field of the view. Normally, this setup has a very small field of view. So our group doing some improvement around these problems. We proposed a new setup based on a microsensor interferometer plus a 4F system here. The microsensor interferometer reduces the optical components and shortens the optical path, while a 4F system can adjust the optical layout that makes the beam splitter never restrict the field of view. We can control the field of view by changing the length. Compared with the multi-channel method, the spatial carrier method has a better phase map quality. And more important, it can achieve a spatial application. It's called the simultaneously dual directional measurement. That's the next part I want to introduce. Shearography is sensitive to the shearing directions. Different shearing direction can bring different patterns, which also means the deformation gradients along different directions. The picture shows 3 different shearing direction patterns here. It's okay for the round defects, but in the case as the picture showing here, the shape of the defects is a slot. Like the crack under the surface, shearing directions could have a serious effect on the measurement. Like the picture showing, the horizontal crack is missing under the X shearing, while the vertical crack is missing under the Y shearing. Thus, we know a simultaneously dual directions measurement is necessary for the fast and precise inspection. Okay, so our group proposed the first setup is based on a multi-wavelength and multi-microsensor interferometer setup. The different wavelength laser will not have cross interference on the CCD camera. So each wavelength can carry one shearing directions information. And at the meantime, different shearing directions also means different carrier frequency. So the spectrum can be easily separated here. On these spectrums, B and C carry the X shearing information, while D and E carry the Y shearing information. But this setup, we can easily find that it is very complicated. The complicated structure is the major issue of this. Our next improvement is to reduce the multiple lasers to a single lasers, because different wavelengths require the compensate calculation and analysis. Okay, that's our second try. The second step proposed by our group is based on the polarized light. Since two light with perpendicular polarized directions will not have cross interference, it is a better carrier compared with multi-wavelengths. Then the next step, we feel this setup is still too complicated. So next step, we want to reduce the optical components. And this is our last try. Our recent setup takes the full advantages of the characteristic of the polarized. This setup not totally separate the two shearing directions into two channels, but we place a public channel which contains 4 polarized directions like here. So the ordinary light only make an interference with the ordinary light, and the extraordinary light always makes the interference with the extraordinary light. So we save a lot of components and reduce the light waste. It enhances the stability. Okay, the last, I want to check some applications here. The left two are the wrapped and unwrapped phase map on an ideal defect board. And the right two pictures are the result of the 3 defects on honeycomb structures. And here, the left two are a round defect and a crack on a board, which are detected by our simultaneously dual directional measurement system. And the right side is a dynamic measurement on the range of the 2 seconds. We can track the gradient change in 2 sharing directions, which is unable for the temporal phase shift method. Okay, the last I want to discuss in some potential and limitations. Spatial phase shift stereography has a big potential on dynamic measurement and simultaneously dual directions measurement. It could substitute temporal phase shift stereography in the future. But before that time, we have a long way to go. First, we need to improve the light usage efficiency. Both two methods have the problem that they require large speckle patterns, which means we need a small actual size. It could reduce a large amount of incident light. As the laser technique, we don't hope the laser power is always under a state loop, right? So besides, the phase map quality needs to improve due to the things we just talked about, the spatial resolution. And also for the spatial carrier method, we have a problem of the spectrum aliasing. So if it's too early for us to put the spatial phase shift method into the industry, but we believe it's a future. And here are some of the reference. If you want to know more details about this technique, you can check the reference here. And the last, thank you. Any questions?
Yeah, thanks, Boyang's presentation. Any questions? Any questions? Hi, Professor Tyler Bell. Do you have any comments?
Hello, can you hear me?
Yeah.
Yeah, I don't have anything in particular, and I don't think we have anything in the chat. I'm excited to see the future potential that you alluded to.
Okay, thank you.
So if no question, and I think Professor Tyler Bell and I highly appreciate all the speakers and attendees. Thank you all for your time and effort for this session.
Yes, thank you very much. Hope to see you all again next year.
Yeah, thanks very much. This session I think is very very good, impressive. Okay. Yeah, thank you all.